Okay, well, we're very happy that Sam Leutheusser, is that right?
Yeah, Leutheusser.
Leutheusser.
Yeah,
Got it. They also be giving the talk on Tuesday. This is the general appetizer for that. Well, I don't think I know your title, but
oh yeah, I'll
not for that.
Yeah.
Right, do it.
So thanks for the invitation to give this extra talk. Hopefully I'll be able to make sense of my title for you by the end of the talk. Okay, so the title of the talk is making sense of local information in quantum gravity. And so here I'll sort of be talking about some things that I've been thinking about over the past few years. I'll try to convince you that, in particular, I've been using various algebraic techniques to try to understand questions related to this issue. And I'll try to convince you that those algebraic techniques are very useful. And let us sort of make sense of the second half of the title. What does it mean? What does it mean to be a local observer in some quantum gravitational system? Sort of observing only part of the degrees of freedom of that system. And in particular, sort of how do we get semi-classical physics? How do we get a semi-classical physics description out of that? Okay, so why is this an interesting question? I think maybe one of the most interesting things that's observed in the past 50 years and stuff is that we currently see that the universe appears to have a positive cosmological constant right now. We're in this era where as far as we can tell we're approaching a de Sitter universe in the future. And so in particular what this means is that if this era continues, then at some point in the future, let me try to draw that less than 55 degrees. At some point in the future, the universe will continue to expand and will continue to expand, and there's going to be a huge portion of it, that we can't see. Good. So even in principle, if we were to make measurements infinitely far into the future with our current understanding of the universe. So here, this is the world line of some co-moving observer, which you could take to be us in some generalized sense. If you imagine that we existed all the way back here, you can imagine that this sort of cutoff surface back here is reheating. And so I'm not going to say anything really about before that. But the point of this is just to say that okay, so back here, way back here in time, there might be some non-perturbative quantum gravitational effects. But in our current understanding of the universe, with the effective field theories that we use at the moment, for all intents and purposes, we're following this approximate geodesic out here. The universe looks like it's going to be de Sitter, and so there's some part of the universe that we're missing. So to describe our experience of the universe, we shouldn't think that we have access to all of the degrees of freedom. In principle, maybe in a quantum gravitational theory that's fully non-perturbatively defined, maybe we do. But at the moment, I think we don't have access to that. Okay, good. And so this sort of motivates us to understand some notion of local physics, even in quantum gravity. So even if quantum gravity is fundamentally non-local at some scale, there's still some notion of local physics, which is the physics that we observe, which maybe is not geometrically realized, but is more we're observing some subset of the degrees of freedom that we see. Okay, so this sort of motivates two questions that are of particular interest. And so the first one is, what's the best framework to describe local physics in a quantum gravitational system? And so this will really be the focus of the talk today. And there's another sort of closely related question, which is, how do classical geometric notions, so here what I drew is a Penrose diagram of a classical spacetime. This is some classical diagram that we believe we can do effective field theory on this diagram, and that describes our experience. But there's a question here that in quantum gravity, if this is fundamentally a theory of some quantum mechanical degrees of freedom that may or may not have geometric interpretations, why is it that this picture works so well? So another way to say that is, how do these sort of classical geometric structures emerge from a fundamentally quantum description? So, if the degrees of freedom in whatever, non-perturbatively complete theory of quantum gravity, if we have some fundamentally quantum degrees of freedom, why does this sort of effective field theory picture work so well? And, how is it that these sort of fundamentally quantum degrees of freedom can describe a picture like this? Good. And so let me say that for today, I'm going to focus sort of on this first point. And then if you're still around on Tuesday, then I'll talk a bit more about the second point of the emergence of classical features. Okay.
Assuming that quantum mechanics is exact.
Yeah. So assuming quantum mechanics is exact. Yeah, that's true.
That part is not emergent.
Not treating quantum mechanics as emergent. No. Yeah, that's a good point. Yeah.
There's like point two is somewhat larger question than this sort of de Sitter issue, right?
Yeah. This is certainly a more general question. Yeah. So for this, And so for this question, I think we have some handle on this in asymptotically ABS spacetimes. Outside of that, it's a bit trickier to say. Whereas this first question, we're going to sort of look at hints from effective field theory and the description to argue that there's sort of an algebraic characterization of that physics that potentially potentially can be related to this second question, and we can understand that algebra from more fundamental degrees of freedom and sort of see where this local physics comes out of. Yeah. Great. Any other questions? Okay. So let me just give a quick outline. Okay, I think as I have mentioned a couple of times, I'm going to try to emphasize that I think an algebraic perspective is very useful to try to understand these kinds of questions. So I'll try to convince you about that in the beginning. Then in particular, I'll talk about the idea of von Neumann algebras, which are just a particular kind of algebra that's closed in a certain topology. And I'll talk about how those algebras are classified and how we can think about that classification in terms of entanglement structure. And that really leads back to this first question where we have these fundamental quantum degrees of freedom that can be entangled in a certain way, and properties of that entanglement structure will give rise to these sort of semi-classical pictures. Good. And then I'll describe some recent work about algebras in semi-classical gravity. Great. And then I'll close with sort of some future reasons. Okay. Okay. So one thing I'm going to try to convince you of is that these algebras are a useful language to understand aspects of quantum gravity. And one of the reasons why this is sort of an important way to look at quantum systems is that it may be that the Hilbert space, so Hilbert space descriptions of this quantum physics, is not fundamental. Usually, when we talk about quantum systems, we say, okay, we have some state vectors, they lie in some Hilbert space, that describes all the possible states of the system. And then, and then we can talk about operators acting on that. We can talk about transition amplitudes and things like that. But what I want to emphasize is that this description of the physics may not be fundamental. And in fact, there are already indications of this just from quantum field theory and curved space. Okay, so good. So in general, so this is sort of really the leading order approximation to quantum gravity when we can have some fixed background spacetime. We take the curvatures small so we can ignore all the quantum effects. Then we end up with this theory of quantum fields on curved spacetime. And if we have a general spacetime subregion, so we can think about general spacetime subregions, something like that might be this diamond, or in higher dimensions, the domain of dependence of the ball. And so we have some local subregion in that case, and we can think about this as sort of being defined by an observer who's on a world line that spans that spans this cone. And in particular, what's true is the following thing, which is that if we take whatever field theory that we're interested in, we can associate, okay, so let's call that diamond D, we can associate an algebra of operators, sort of just as an abstract object, just describing the operations that can be done by the observer in that diamond, or more generally in some space-time subregion. So this is something that we can do, and we can think about this as being something that is just sort of defined in terms of the field theory that we're studying. A scalar field theory. This might be phi of f smeared against some test function that's in here. There might be a theory with fermions. You'll have these fermion operators, fermion bilinears. And so this algebra sort of we can think of as being described from an overarching quantum field theory structure. But what I want to emphasize is that the Hilbert space that you get when I try to represent this abstract algebra as operators on a Hilbert space, that Hilbert space can be different depending on various choices that I make. Good. So this is sort of a general phenomenon in quantum fields and curved spacetime that if I try to define some subregion, maybe I'm thinking of this is the sort of fundamental observer that I want to take as being there, and I want to quantize the theory with respect to the observations that they see. And so in general, it makes sense, just at the field theory level to assign the algebra, but I can end up with different Hilbert space descriptions. Okay, so that's sort of a general phenomenon. The simplest example of this, which you may be familiar with, is just the example of Rindler space. So I don't even really have to go to curved spacetime to see this phenomenon. So yeah, so just for a concrete example of these things that I'm talking about, imagine that I give some Rindler decomposition of Minkowski space. So here's x greater than 0 and its causal completion, and x less than 0 and its causal completion. Well, if I have some field theory, I can associate this abstract operator algebra here. And I can think of this as sort of like, so imagine I had some scalar field theory. If I have some region here where a function, test function f is supported in that region, then I can think about this as the algebra generated by operators phi of x smeared against that test function. Okay, and so these operators form what's called a star algebra. It's not super important what that is. It just has adjoints. But importantly, this is not yet a von Neumann algebra. This is just some abstract algebra of operators that I can multiply. I can take linear combinations in this subregion here. Okay, so this is some sort of this is some sort of abstract mathematical object. And then usually when we want to discuss quantum field theory, then we want to represent it on a Hilbert space. On some Hilbert space H. So what happens when we try to do that? Well, imagine that you're only given access to this algebra here, A right. There's a very natural, maybe this diagram's getting too busy. There's a very natural state to consider on this algebra. And that's a state that if you imagine here, I'm drawing the Rindler boost time beta. So if there's a very natural state to define on this algebra that I'll write as 0R, which is what people call the Rindler vacuum, and it satisfies the following property, which is that if I smear this, and then you can just have your spatial directions, good, if I do that, that's 0, it's greater than 0. So this is a state that only has positive frequency modes with respect to this notion of Rindler time. Okay, good. And a wonderful thing about in algebraic quantum field theory is there's something called the GNS construction. Oh, and I should have said, yeah, feel free to interrupt me with questions if you have questions at any point. There's something called the GNS construction, which takes this algebra A right and this state 0 right, and then spits out for you a Hilbert space that I'll call H rind in this setting. Okay, and so in particular, so this just tells you that I can find, I have my abstract algebra. I can define a state, which from the algebraic perspective is just some linear functional from the algebra to the complex numbers. It takes the operators and spits out a complex number. That's the notion of an algebraic state. And then there's also I can do this so-called Gelfand-Neymark-Siegel construction to obtain a Hilbert space representation of that algebra. So to take this abstract algebra and write it as sort of a concrete algebra of operators on the Hilbert space.
Is it unique?
Sorry?
Is that unique?
No. So this is not unique. This is very highly state dependent. So the choice of state that I choose on the algebra will give me very different answers over here. Yes.
I guess is the condition on that the ground state unique? Does that uniquely define the ground state?
Does this uniquely define the ground state? That's a good question. So in free field theory, it certainly does. I'm not sure outside of that.
But you're not trying to do this as a state in free field theory. You want to use this GNS construction.
Yeah, I want to use this GNS. Yeah, that's a good question. I'm not sure at the moment whether this is enough to completely fix the state.
Can I ask you, like, what niceties assumptions does one typically have to make about AR? Because so in other words, is this smeared field like you just wrote nice enough, or does it need to be?
Oh, the smeared field is nice enough. So at this point, they don't need to be bounded operators at this point. So in the end, they'll only be densely defined on this Hilbert space. But yeah, so it took a long time though for that to be realized. So originally, I think it was done. I think actually the GNS construction formally requires these operators that at least you have to have a norm on the algebra. And so you need some bounded operators. But then it was much later realized that you can still do it with the star algebra structure. Technically, then there's also, so usually people talk about the GNS construction as a triple. They say you have an algebra, you have a state, and you have a Hilbert space. When you start with a star algebra, really it's a quadruple. You have an algebra, you have a state, you have a dense subspace where the operators are defined, and then you have the full Hilbert space. Yeah, but it can be done. Yeah, great. Anything else at this point?
So at this point, there's not yet a relationship to the Hilbert space in Minkowski space.
No. There's not yet a relationship. That will be the next thing that I'll talk about.
And the fact that the Rindler vacuum is singular in a real sense that's not at this point an issue.
So at this point, it's not an issue, but it will come up. It will come up very soon, actually. Yeah. At this point, it's not an issue. Yeah. So we can still do this with the. So here at this point, the Rindler vacuum makes perfect sense. And on these star algebras, it defines correlation functions that make perfect sense and describe the physics locally in that subregion. But there's a sense in which you really can't think of this as being a subregion of Minkowski space anymore. Really, all you've done is effectively put in some infinite shockwave here and separated off Rindler space as its own theory, its own globally hyperbolic spacetime in its own right. Good. Okay, yeah, so that's the point I'll come to now. Okay, so yeah, let me just say this. So okay, why do we like these Hilbert spaces? We get these concrete representations of the operator algebra. Good, and I should define this here. Okay, so we get so pi. I'll use these pi's just to denote the representations. That's just this map from the algebra to operators on this Hilbert space. Then I'll also write this sort of double prime symbol a lot. So what does that mean? This is what's called the double commutant, which is applying, okay, so this is the double commutant, okay, so what's the single commutant? Yeah, so I can do this commutant operation whenever I have a Hilbert space representation of the operators. And what that is I just, so imagine I have some set of operators here. It doesn't even have to be an algebra. Then the commutant is defined in the following way. It's the set of B that are bounded operators on the Hilbert space such that they commute BA to B for all A in A.
So A doesn't need to be bounded, but A prime is always bounded.
Yeah, exactly. So this can take just a set of unbounded operators, but it will spit out for you an algebra of bounded operators. And so that's the important point. So these double primes are going to be all over the place because this gives me a von Neumann algebra of bounded operators. They're defined on the entire Hilbert space, and I don't have to worry about these domain issues. Yeah. And so what's the use of the commutant? Well, the commutant of any set is always a von Neumann algebra. And so then the double commutant is just I do the commutant again, and that gives me another von Neumann algebra. Von Neumann algebras are useful because they're classified in certain ways, as I'll argue in terms of their entanglement structure. And they're closed under a very natural limit, which is taking these matrix elements. So if I imagine I have a sequence of operators, and I want the matrix elements of those operators to be well defined as I take the limits. And so I define those elements through the limits of matrix elements. So it's sort of a very natural topology that I don't want to get into too much detail about. But yeah, I'll just say these von Neumann algebras are useful. They're particularly useful if you ever want to talk about sort of quantum information theoretic things in quantum field theory.
So the idea is that the double commutant is sort of a nice subset of the original.
Yeah.
But,
so
like if you apply to this free field or the smear free field, like is there any idea of what it gives you?
Yeah. So there is an idea. So in particular, so usually, so in the free field setting, this can be understood very, very sort of concretely, which is that if I start with my field phi, smeared against F, then I can construct what's called a C-star algebra, the Weil algebra, by taking formally these exponentials. Okay, so this, you can't think of this as a real exponential because it doesn't converge in the topology on this, but formally there's this exponential, you can think of it as this exponential here, which is the so-called Weil algebra. And then that's a C-star algebra that admits various representations. And then it can be closed into a von Neumann algebra. So here, when I was just talking about the star algebra, none of the elements of A are actually elements of this algebra because they're not bounded necessarily. But here, these are nice unitary operators. And so these end up being elements of the algebra, but I also get some additional elements when I do this closure in the sweep topology.
But these look like very far from the things that we're usually discussing. So is there a sense that if we know about those, we know about everything else, or is this very restrictive?
Yeah. Oh, sorry. So going to the von Neumann algebra, is that restrictive?
Yeah,
it is restrictive in a sense that I'll describe. Okay. So like the operators that you get from this closure are crazy operators from the perspective of the algebra you started with. They're really crazy. But from the perspective of the Hilbert space, they're very nice operators. So for example, like imagine even if I just had this field theory, constructing the projector onto the vacuum state from these field operators is very difficult and stuff. But that's an operator that's very naturally in the von Neumann algebra. But of course,
How lossy is this? Like, what kind of questions do you not get to ask once you restrict to the? Or is there a sense that it sort of gives you access to almost everything?
It gives you access to almost everything. What I want to say is that the point that I'm going to try to argue is that once you do this closure into the Hilbert space, it's like fixing a particular space-time that your algebra is working on. So before I had this abstract algebra for which I only had to define the geometry of the space-time for these operators in the region that I'm considering. As soon as I go to the von Neumann algebra, I'm restricting roughly what the von Neumann algebra is restricting to a restricted allowed set of states that I'm going to allow in the algebra. And those are all states that have a particular, if I want to think of this as embedded in a space-time, they have a particular space-time structure also outside of the diamond. So you can no longer think about the diamond as its own independent system once you've done this. Yeah, so that's the restriction that you use, that you lose, yeah.
By the way, you have a relation, I guess, between like the commute and the level of the algebra and like the complement of this diamond, the causality.
Oh yes, yeah. So in the usual setting, yeah, let's say that we have this diamond. Then there's some region that is kind of hard to draw, but it's the rotation of that region out there. That would be d prime. And so usually in algebraic quantum field theory, I would have to say, okay, without the Hilbert space representation, all I can say is that the operators in here have to commute with the operators in there. If I do the Hilbert space representation, so imagine that I've chosen my Hilbert space, then I have this, then I have the following relation that this is in A. Okay, good, sorry, I should explain everything here. Okay, so this would be the von Neumann algebra closure of this algebra in the diamond that I started with. And that has to be a sub-algebra of all of the operators that commute with all of the operators in this causal complement D prime. So this is the usual statement of causality in algebraic quantum field theory. And this may or may not be saturated. In lots of cases it is, in some cases it isn't. But I'll actually talk about that on Tuesday. Yeah. Great.
In quantum field theory, there's no reason why it should be saturated.
Yeah, in quantum field theory, so a quick example is theories with global symmetries will not satisfy this. That's a very quick example, yeah.
Well, there's also theories for which all of these algebra are empty, like topological field.
Oh yeah, that's true, yeah, that's true. Yeah, so I should say, like this algebraic framework is very useful for sort of like for local physics. It's not great for non-local physics, yeah. Good. But there has been some sort of understanding of how to take those into account more recently. Great. Good. Okay. So I was talking about this example. So sorry. Let me just define this von Neumann algebra that I get from closing this representation on the Rindler-Hilbert space as this MR0. Okay. So that is some von Neumann algebra. Good. And right. And so, so what I wanted to say is the following, which is that if you think about this sort of A, R, this triple, H rimmed. So this sort of gives a satisfactory mathematical definition of the physics in this region here, in this Rindler region here. So this, it gives us a Hilbert space representation of those operators. It lets us talk about the physics that's happening in that subregion here. Okay, but if you're somebody who knows about the fact that you have the rest of the Minkowski space here, maybe this choice of condition of the Rindler vacuum is not a very natural choice. A much more natural choice of vacuum would have been a vacuum with respect to inertial time. And so this is the Minkowski vacuum. Okay, so a very natural choice is just the Minkowski vacuum. The vacuum that realizes all the symmetries of the Minkowski spacetime. So if we write that as omega for the Minkowski vacuum, well, again, I still have this algebra of Rindler operators, so I can take these two objects and now perform the GNS construction again. And that gives me a new Hilbert space and a new representation of that algebra on the Hilbert space. And in particular, so let me define omega.
Now you actually mean literally take the VAV in the Minkowski vacuum.
Yes, yeah, to define the state. Yes, yeah. Good. Good. And so this furnishes another representation. And a very famous fact about quantum field theory in these infinite dimensional algebras is that these representations, this pi Mink, and pi rind are unitarily inequivalent. So I can represent them on these Hilbert space, but I can't find a unitary that's going to take me from one representation into the other. So this is sort of a famous fact about these sort of infinite dimensional algebras. Good. Okay. And so good. And so, but this gives me another description of the physics in that region R, in this Rindler subregion. And so I have some triple again. They are now the Minkowski vacuum and H min. And this gives another satisfactory description of the physics in this region R. But crucially, these representations are unitarily inequivalent. There's a very technical way to say this that I'll try to detechnicalize a little bit later, which is the idea, oh, that's the wrong one, that this algebra here that I got from closing that representation is what's called a type 3-1 von Neumann algebra, whereas this algebra that I get here is what's called a type 1 von Neumann algebra. So these von Neumann algebras are classified. They were classified by Murray and von Neumann in the 30s, and then in the 70s, where people put some subscripts on them to describe different properties. And so in particular, this sort of provides a sharp distinction between these two between these two different quantizations of the physics in the Rindler range. And in particular, what we'll see is that in this Minkowski vacuum picture, we have this sort of smooth, we have this notion of the rest of the Minkowski spacetime. It makes sense to talk about operators or observers or whatever that fall across that horizon, this Rindler horizon, into this future region here. Whereas in this sense, there's kind of an infinite shock that separates out this space-time from the rest of it, and it doesn't really make sense to even think of this as a subregion of Minkowski space anymore. So that's related to the fact that they're non-normalizable states. If you think about it like so, in free field theory, you can do this really, really explicitly. You can just write down these two different vacua, and what you find is that this vacuum, this so-called Rindler vacuum, which would be a sort of as a squeeze state between the left and the right theory, what you find is that is not a normalizable state. Oh, sorry. The Minkowski vacuum is the squeeze state of the Rindler vacua. Good. Okay.
What does this shock that you? What's it? So there's something kind of physical about this shock.
Yeah. So the physical thing about this shock is it's just, I mean, if you imagine that you have some field theory, then the stress tensor. Let me give these guys names. So I want to call that direction V and that direction U. Okay. So if I put null coordinates on this, then the physical meaning and why I say that's a shock is that it's. So I want to go that way. I think it is. As I defined it here, this would be T U U is infinity. So the stress tensor has this divergence in terms of a flux crossing in this direction.
And that's some delta function localized on the light cone. Or is it leaking into?
I think it leaks in. It leaks in. Even if you go close, yeah. Even if you get close to this edge, I think it will leak.
I think so. It blows up.
Yeah. So it blows up. Yeah. Yeah.
What sets the scale at which it blows up?
That's a good question.
Dimensional masses.
Yeah, in this example, I'm not sure.
There's no scale in the problem.
The distance for the.
This.
Oh, you mean it blows like up like 1 over
Power
distance
density.
squares or something?
Yeah. It's something like that. Yeah. This is just sort of. Yeah.
The origin is a preferred point here.
Yeah. Here you've chosen a preferred point, and you have the
It's not a small effect that's localized near the shock. It leaks everywhere into.
Yeah.
So there's no place where this is a good approximation to.
No. Yeah. It's never a good approximation. Yeah. None of the so let me say sorry. Yeah. None of the states in this Hilbert space. So okay, if I imagine trying to recreate Minkowski space from this discussion, I'd also put in the left algebra and do the same thing with the GNS there, and then I'd have a tensor product of them. None of the states in that Hilbert space are finite energy with respect to this Hamiltonian, the inertial Hamilton. Yeah. So everywhere it's bad. Yeah.
is it something like modular, but like if I have like a system which is type 1 and some density matrix is gonna purify it to something bigger, or just like really like this in terms of double state? Or
So you can usually actually do it in the other direction. So one of the confusing things is that, okay, there's a sense in which the type 1 algebras are bigger than the type 3 algebras. And maybe one way to say that is just, oh, I drew this the wrong way, but yeah, okay. One way to say that is that just this subregion will have this type 3-1 algebra, but if I take the operators everywhere in Minkowski space, that gives me a type 1 algebra. And so this sort of subregion, so the Minkowski vacuum purifies the thermal state that I would get here, that's basically the Unruh effect. It purifies the thermal state that I would get here. Now, really, purification is not the right way to say this because these type 3-1 algebras do not admit density matrices. There's really, they don't admit traces, they don't admit density matrices. So there's this physics. Once I've closed this into a type 3 algebra, there's no sense in which I can forget about the fact that the left side is there. The left side has to be there. Whereas in this setting, there's I can throw in a left side if I want, but then there's no sense in which the future and past regions are there because I'm always going to blow up if I try to cross those horizons. Good. Any other questions? Okay. Great. Good. Okay. So yeah. Okay. So one thing that I've sort of been trying to emphasize here is that sort of the field content of the field theory gives us this abstract algebra A of R, and this is some sort of overarching structure. So there's a sense that, if I imagine just taking some scalar field theory or something and looking at smeared field operators in the algebra they generate in this region, that's a thing that's sort of well defined without the choice of a Hilbert space, and could be what we mean by talking about a field theory in that particular globally hyperbolic spacetime, which is this Rindler wedge. And so there's this overarching structure of the algebra that we get from the field theory, but when we try to go to a Hilbert space representation, then we've had to make some choices. And so in particular, so from this algebraic perspective, the space-time, by this I mean, also the space-time outside of the region that I started with, is tied to the choice of representation. Good. So there's this overarching structure which there's the algebra. This is tied to the choice of representation, which is the choice of Hilbert space. Okay. Good. So all this is to say that even from this analysis, it might be that the Hilbert space is sort of not a fundamental description. A fundamental of the description. There's sort of a more fundamental description in terms of some overarching algebraic structure. And this is so this I've given to you in this example with quantum fields and curved spacetime. But this is, maybe you would think of it as, it might be a desirable feature if we wanted to talk about quantum gravity. Because in quantum gravity, the spacetime itself is supposed to fluctuate. We're not supposed to have any specific background geometry on which we're describing it outside of any particular limits. So if we treat all the parameters as finite, then we might not want to have a fixed spacetime. And so the idea is that maybe these algebraic structures can give rise to a description that's background independent in the sense that we don't have to specify exactly which spacetime we're working on. And so that's sort of one of the goals of this program. And it's not something that we completely understand yet, but we can understand it in some specific cases. So let me just say that, I think it's this one. Yeah, that with Honglu, I tried to understand this in the context of ADS CFT. And what we saw there is that you get these sort of semi-classical geometries that come out of taking the large n limit in the boundary theory, And what you find is that the Hilbert space of the CFT, it fragments when you try to take this limit. It fragments into disjoint disjoint pieces that describe different asymptotically ADS background geometries in this case. Describe. Okay, so this is something that we think we can understand in the large N limit of ADS CFT, where we get these, where there in that case we have a more fundamental quantum description of the theory. And if you look at what happens to the Hilbert space as you try to take the large N limit and define some algebra of operators, what you find is that you get this sort of splitting where the Hilbert space fragments into all these different disjoint pieces that are describing different semi-classical physics. Good, and so that's in the ADS case. And then I should also say that last year, Ed Witten tried to describe this in a more general setting. Basically, erase that picture in a more general setting in which the only sort of structure that we try to put in is the algebra of observations on an inextendable world line. And so there's sort of a more general story in that direction there that I won't discuss too much. Okay, are there any questions at this point? That's sort of the, so hopefully you think algebras are somewhat useful. Now I'll talk more about what are these von Neumann algebras in the first place.
Yeah, that's something, maybe you said this before, but all these explicit constructions of algebra have been done, you said, for free field theory. Or have they also been done explicitly even interacting field theories?
They're certainly most explicitly in free field theory. There are certain cases in which I think it can be done in interacting theory, but the general sort of map from field to bounded operators is more complicated. I mean, so you can do the formal thing, which is that you can define these von Neumann algebras in terms of the spectral projections of those operators, and so that gives a satisfactory definition, but it's not very explicit.
Can you elaborate just a little bit on that?
Oh yeah, I think so I think this is okay. The key of von Neumann algebra, one of the important things about von Neumann algebras is that any operator in a von Neumann algebra can be written as a sum of a bunch of projections, and so that lets us write something like that will let us write something like we have phi of f. Then this will be some integral. Let me say there's some dE. What's the usual notation for this? I think it's usually written in this way, and then let's say like this. So there's this usual idea that if I have some field, then I can decompose it at least in terms of these operators that have these sort of definite space-time quantum numbers. These are called the spectral projections, and these spectral projections, sort of by definition, they're projections, and so they're bounded operators. And so the way that you're supposed to define the von Neumann algebra for local operators in this case is by decomposing this in terms of just the spectral projectors that show up there. But I think it's something that's not, I would say, completely well understood. Yeah.
So am I entitled to say that, would it be incorrect to say that this is a form? Why can't I say that this formulation only goes for free field theories and not for interactive field theory?
Well, so this formulation will hold for interacting field theories. It's sort of it's nice because it gives like a field system independent characterization of the algebra and stuff. The big drawback is that it's usually not very explicit. For free field theories, it can be made explicit, and for interacting field theories, it can't really in general. Yeah. And okay, any other questions at this point? Okay, great. Let's go here.
Maybe just one more since I was
Yeah.
just thinking about it. I mean, you gave these two examples, right? One with a shockwave and one that continued it. But in principle, more choices of vacuum in the GNS construction will give me more, presumably more examples of kind of shockwave type
Yeah,
states with different properties.
yeah, I think in principle that's true. That if you the issue is coming up with these what those states are. So here we had a nice natural choice of state that gave us a nice sort of smooth shockwave free, and we had another choice of state that was somewhat natural, I guess, from the local perspective, and it gave us this horrible shockwave. But in principle, there are many more states we could have defined on that algebra, but I think none of them are unnatural, and they might give rise to different notions of this shock geometry.
In principle, all of them are kind of allowed though, right? I can take any functional.
Yeah. They're all, yeah. You can take any linear functional norm one, usually you want it to be normal on the algebra. And those are all really allowed. But going to the von Neumann algebra, what you do is throw out a huge amount of those states. You basically say, I started with this state that I used in the GNS construction, and you don't allow anything that's very singular with respect to that state. Yeah.
Sorry, what's the chicken and the egg?
Oh, sorry.
So you pick the state first, or you go to the von Neumann algebra first?
So I would say you pick the state, and that gives you a von Neumann algebra. Like you start with this sort of abstract star algebra,
Okay.
and then I pick a state and I do a GNS representation, and and then that gives me a von Neumann algebra when I close it. But now that von Neumann algebra, things that even though as a sub algebra, well, okay, even though at this, okay, so this is always true. Really, I should have pies here, but okay. If I imagine I represent this algebra on the Hilbert space, so I have this original algebra. Okay, to say it's a subset. I should have gone to the C star algebra. I should have exponentiated the operators so that they're bounded. But the usual word people say is affiliated to. The operators in this algebra are affiliated to the operators in this because I can take bounded functions of those operators and then they're elements of this. And so what I do is I would have some. Good. So I have these two different representations, and good. Now this is just if it's a faithful representation, then this is just equivalent to the algebra that I started with. But this thing is not equivalent to the algebra that I started with. It has these extra operators that are added in by this double commutant operation. And so there are linear functionals on the algebra. There are algebraic states. There might be some omega 1 that makes sense on pi of AR, that's well defined, but it will not make sense as an algebraic state on this. So here it won't make sense. And so there's a sense in which I lose, in which I've lost a bunch of states I was originally allowed by going to the von Neumann algebra.
What is omega?
Sorry, omega is an algebraic state. I should have, yeah. So omega, you could think about like in this case, it would have been like literally this omega dot, this omega, where this is an element of. Yeah. Sorry. Algebraic states are basically just defined by these linear functionals, which you can then GNS represent them, and you get a vector state in a Hilbert space that realizes that linear functional. Yeah.
But in general, there's no sense in which you get something that's quite as good as in Minkowski space, where you get the whole space, and it's just bigger. So the algebra is bigger, the state space is
yes,
smaller,
algebra is bigger, state space is smaller.
but
yeah.
you don't quite know maybe in general how small or how big, or is there some idea about it?
Yeah, I think in general, you don't know, how much smaller or how much bigger. I don't know if there's a good quantitative characterization of that.
It just as a random question, would it have been logically possible that you don't get all of Minkowski space, but just a bigger wedge or something?
That's a good question. I do think it's a logical possibility that I can't rule out. But I think because yeah, so you're imagining that, like, imagine that we got up to here
Yeah.
or something. Yeah. Then I think roughly because in this well, that's a good question. Okay, so the real answer is I don't know. But this would be very strange because in principle, any of the states that any state that I specified on here, I can use an operator in this larger region. I can use an operator in this larger region to sort of completely fix the state in the smaller region, just to be the Minkowski vacuum. So I think I would be very surprised if you could do something where you get only a part that you get something that's a little bit larger, but not the whole Minkowski region larger.
Some of the ideas that the moment you go through the singular point, you get everything on the left
Yeah,
by reconstruction.
yeah. So I certainly don't have a proof of that, but I think that would not be possible to realize. Yeah.
But in more complicated settings,
Yeah, that's true. In more complicated settings, it might show up. Yeah.
Would it be in tension with the causality criteria presented, like, I mean, the relation between like the algebra is commutant and the causal region of this algebra?
Oh, right. Sorry. So in this, yeah, I guess in this setting, so okay, imagine if I got this larger Rindler wedge, then I think in this setting, yeah, okay, that's a good question. So, and yeah, so let me just say, in principle, what's always true is that when I go to the von Neumann algebra, these type 3-1 algebras, they don't admit irreducible representations. Whenever I represent them on a Hilbert space, I get a commutant that is another type 3-1 algebra. And so in principle, the algebra in this subregion here is a type 3-1 von Neumann algebra. So it's possible that, within this spacetime, this region, if we imagine we forget the left and we just have this extended thing, within this spacetime, this region is the causal complement of that region. And so everything there had better commute. And in principle, I can get a type 3-1 algebra there. So I think it can be consistent with causality. Yeah.
Maybe it's not, but there's a larger thing. That's not just the Riddler state associated with different choice of origin.
Oh yeah. Sorry, yeah. This larger thing is a Rindler with a different choice of origin.
So the same, you couldn't get it. I understood.
Oh, right. Oh, sorry. Okay, so right. Okay. So certainly I can define a state that has the shock here, and then talk about this subalgebra here. What that state looks like on this subregion, I'm not 100% sure. Yeah, but in principle, one could imagine defining the Rindler vacuum with respect to the boost around that point. That's some state. It defines a state on this whole bigger algebra that covers everything out here. And so therefore it also defines a state on this smaller algebra. Yeah, okay. So maybe the fine details then of that state will give me something that has the shock wave. Yeah, that's a good point. Yeah. Good. Okay. Any other questions? Okay, great. Good. Okay, so let me try to say something about the entanglement and von Neumann algebras. Okay. Good. Okay, so let me remind you that I wrote what I just wrote in that last example was that this was a type 3-1 von Neumann algebra, and this was a type 1 von Neumann algebra. Okay, good. And I wanted to emphasize that you should really think of these as being algebras that are defined on different space-times. And in particular, this what we'll see is that these algebraic types are very can be sort of closely related to the to this idea from let's see, the idea of ER equals EPR. So there's so good. Okay. So yeah, what I want to argue is following. Okay, so these papers said, okay, maybe there's a connection between entanglement structure, and yeah. So these are the papers that are about the idea of ER equals EPR, which is the idea that there's some entanglement structure, and that's related to a space-time connectivity. Good. So that's the idea. And yeah, let me say that this will give these algebras give sort of a refined notion of this idea, and sort of describe how this works. Yeah. Question. Okay. Yeah. Okay. Great. Okay. So let me say yeah. So this was the original proposal, was that in the context of an ADS black hole, which is described on the boundary by a thermal field double state between the two boundaries. The idea that this state has a huge amount of entanglement, which is what gives rise to the fact that that slice is this Einstein-Rosen bridge. Okay. And so let me say this has been recently been algebraically characterized. Okay, and so in the causal case, this was done with I did this with Hong Lu in 2021, and then in the spatial case, this was done Engelhardt. Okay, good. And so what I mean by this is that the idea that there's enough entanglement in this picture for an observer to jump across the horizon and meet up and be sensitive to any excitation that happened on the left. This is what I mean by this causal characterization. Whereas understanding this on a single spatial slice took a bit more work and was done in that paper. Okay.
So this is like just field theory on the fixed background, or mix of this, or are you thinking about it?
Good. Sorry. So yeah. So this is field theory on a fixed background. This one you have to think a bit more about quantum gravity in order to do that, because there they were interested. They were interested in these evaporating black hole setups where you have this transition in the quantum extremal surface, and so in that case, yeah, you need to think more about the gravitational effects that let you this transition to happen. Good. Okay. And so all this is to say is that there's this idea that's been going around that entanglement somehow should be related to space-time connectivity. And what I want to argue is that these von Neumann algebras, these von Neumann algebras encode detailed entanglement structure. And the fact that they encode detailed entanglement structure can be thought of as sort of a realization of this. The fact that they encode detailed entanglement structure is what allows for us to give a space-time description in which an observer can jump across and see the other side, or in this more complicated case, to see that the spatial slice is connected between two asymptotic regions. Okay. Okay, so how does this work? So I've said a few times these math classifications of type 1, I guess I've only actually talked about type 1 and type 3 so far, algebras. And so let me just give an example that shows that this is related That date is probably wrong, but yeah, there's these so-called Iraqi woods constructions that are from back in the day that tell us that sort of tell us that make really precise in what's called the hyperfinite case that these von Neumann algebras are related to entanglement structure. Okay, so what I want you to imagine here is that imagine that I just have an infinite chain of entangled spins. So here, I have some spin that I'll call the left, and here I'll have a spin I'll call the right. And these are all entangled in some states. And so it's a product state between each pair, but each pair is entangled amongst itself in the following way. Okay, good. So let's think about, imagine trying to cut off this Hilbert space, up to the nth spin. Well, then what's the dimension of the Hilbert space? Well, it's growing like 4 to the n. So when I take the n to infinity limit to really consider an infinite chain, this is uncountable. And so what it means is that the Hilbert space that I would get by doing the naive tensor products of the Hilbert space for each of these pairs is uncountable. It's what's called a non-separable Hilbert space. Usually, non-separable Hilbert spaces are quite unwieldy, and usually they don't really show up in physics. And so what von Neumann, this is called a von Neumann tensor product. But what these people considered is instead, let's see if I can define some of these infinite dimensional algebras using this setting. And so in particular, what you might want to do is think about the algebra. You want an algebra that's spanned, but that's spanned by operators of the following form. So you take the tensor product. Maybe I should make that. Good. Okay. So imagine that I'm allowed to take any finite product of operators, sort of on each of these spins up to some value n. If I allow this for for all natural n, so it's any finite product, then this sort of defines for me an algebra that's acting on this Hilbert space. But the point is it doesn't access the entire Hilbert space. Imagine if I start with some state capital psi. So, okay, let's call this state capital psi. If I start with this state capital psi, that's this infinite tensor product. When I apply, so this is the set. When I apply A to the state psi, because I always, no matter what operator I applied, I had to stop at some finite point. There's an infinite tail of the state psi that's completely unchanged. And so what that means is that these operators, the set of states that I get like this, even when I close this doesn't give me the whole Hilbert space. So I don't end up at this non-separable setting that's undesirable, but instead what I get is, well, I'll write this H set psi, which is a separable Hilbert space. And then I can take these, I can realize, these operators acting on those states, and I can close it in the appropriate norm and define a von Neumann algebra. And the key.
Sorry, n is fixed or?
Oh, sorry. So it's any finite n.
Okay, but you're not changing it. You pick it once and for all.
No, you are allowed to change n. Yeah, you are allowed to change n. Just any operator has to be sort of approximated by some operator where I truncate at a finite n.
Okay.
Yeah. Good. So the type depends on psi, and more formally, it really depends on the infinite tail of psi, because that's when I close this von Neumann algebra into a von Neumann algebra. So what I should have said is I'm going to get some representation of that algebra, and I'm going to close it in this separable Hilbert space. And when I do that, the type of that von Neumann algebra depends on psi. Okay. Good. And so when I complete this algebra in this way, the type depends on the state psi, and more specifically, it depends on the asymptotic entanglement structure of the state psi. So in particular, I get a type 1 algebra if psi I goes if psi I is roughly equal to right. So left. if this goes to a product state, as I goes to infinity. So if in this state that I started with, the tail becomes disentangled sufficiently rapidly, the algebra that I get is type 1. If psi I goes to an EPR pair, as I goes to infinity. So if this tail of this state converges to be an EPR pair, that's a maximally entangled state in the left and the right qubits. As I goes to infinity, I get what's called a type 2 von Neumann algebra. And in any other case, I get what's called a type 3 von Neumann algebra. And the one that I'll mention, because I don't want to talk about the other subscript, is if there's no limit to the von Neumann entropy of the state psi I, of the state psi I on the algebra, which in this case would be B of H I. So that's just saying if I work on, I take the algebra of these qubits, as I go up to infinity, you know, these states are entangled. If they're von Neumann entropies, if there's no limit to the von Neumann entropy, then I get one of these type 3 von Neumann algebras. So what this means is, so what I want to emphasize here is that these types of von Neumann algebras are very sensitive to the entanglement structure of the states that are allowed on them. So this thing admits states that are factorized sort of between the right and the left, because as I go off to infinity, eventually I just get rid of the entanglement. They'll have some finite entropy that I can always get rid of by acting with, you know, non-unitary operators, but operators on a finite number of sites. In this case, all of the states become this EPR pair as I go to infinity. That will be important in a little bit. The fact that it has what I want to emphasize about that is this has a very regular structure. So sure, this is a maximally entangled state as I'm going off to infinity. So it has some huge, if I imagine trying to, you know, compute the von Neumann entropy going up to some finite n, and my states all look like that at the end, then this is going to be diverging very, very badly. But it's diverging in a very regular way that can be renormalized. And so that's what's crucial in this case. There's a sense in which this has a renormalizable von Neumann entropy. And then finally, in these type 3 cases, the entanglement pattern is so irregular that there's sort of no way to renormalize any of the notions of entropy I would have from cutting this off at finite n. Good.
Do you mean like for all practical purposes, or like literally you cannot?
Literally you cannot. Yeah. So there's a theorem that like this von Neumann entropy is literally infinite and cannot be defined in a nice way. Yeah.
Is that because it diverges more rapidly than before, or because it doesn't have a limit?
Because it doesn't have a limit. Yeah. So this actually diverges the most rapidly because it's maximally entangled.
Linearly with n or something.
Yeah. So this will go like n log 2. Yeah. Whereas this will have some of, you know, each one of these psi i's will give an entropy that's less than log 2, but because it's so irregular, there's a sense in which it can be removed. Yeah. Good. Good. Okay, and yeah, so let me just say that, yeah, so for this causal, for this idea of this causal, yeah, so why is this related to this idea of ER equals EPR? Is that what we showed in this paper is that in order to construct notions of time, notions of infalling time, here it was from the boundary perspective. So the boundary, you can think about ADS-CFT as it's kind of morally realizing a construction like this. At any finite n, we have some nice CFT Hilbert space for the left and the right CFTs in this picture. And so at any finite n, it makes sense to talk about the entanglement entropy between those two CFTs in a given state. In this case, it would be the thermal field double. But what happens is that in the large n limit, basically you get exactly these infinite tails of entanglement that cannot be removed even by joint operations between the left and the right regions. And so what we argued was that when n goes to infinity, here this CFT algebra on the entire space-time. So this is different from what I was talking about before with the local physics. When normally the algebra of operators on the entire space-time is of type 1, but in this limit, the way that you define it, even the algebra of the entire space-time, of the entire is type 3.1. And so that's because of the complicated entanglement structure of the thermofield double. And what that allows you to do is realize that entanglement structure geometrically in terms of this picture, where I can have a sharp horizon, observers can jump in, cross the horizon, and most importantly, the notion of a sharp horizon is that the observer who jumps in is completely insensitive to any perturbation on this size for a finite amount of time, and then they become sensitive. And the key is that they're sensitive to it for a finite amount of time, and one can argue that this is the kind of thing that really only happens in these type 3.1 von Neumann algebras.
Yeah, very basic question, but if as I go to infinity, just alternating between fully entangled and fully unentangled, shouldn't that also be renormalizable in the sense that it's just half of that?
So that's if you choose to take the limit in a particular way, where you're sort of skipping each thing.
Okay.
If you're skipping every other one, but the thing is, if you take the limit in a different way, you're going to get a different answer.
Okay, good.
So that's the sense in which it's not regularizable, right?
Okay, so then it would go as type 3.
Then it would be type 3. Yes. Yeah.
Thank you.
Yes. In that case, I think it would be one of these weirder type 3s, but it would still be type 3. Yes. Yeah.
Can you repeat again like the relation between this picture and the fact that this is type 3?
Yeah. Right. So the fact that this is type 3 is related to this picture in the following way. What do I want to say? Okay. Yeah. In this picture. Right. Yeah. Okay. When the algebra is of type 3.1, we can construct a family of unitary operators that describes infalling trajectories that start in the right region and cross the horizon. From the bulk, if you just took the bulk picture at face value, you would say, well, of course I can do that. I can just find some operators in the bulk theory that generate the flow. But what we can do is, because you notice this transition in the type of von Neumann algebra on the boundary, you can actually argue that there are operators you can construct in the boundary theory that strictly you can only construct them in the n to infinity limit that describe that flow. And then there are general theorems of, I think it's Borcher's, that say that kind of flow is only possible if the algebra is of type 3.1. So it's a bit technical.
Can you look at the suboperators as like modular Hamiltonians?
Yeah. So
The generators of
so the generators, they can be constructed from modular Hamiltonians. So in this setting, so imagine this is, okay, here's infinity and minus infinity. In this setting, we can define, so there's an algebra, I'll talk more about this on Tuesday, but there's an algebra of the full R, which is this full region. But there are also algebras associated to semi-infinite time intervals. And so there's, what we call it, a semi. There's an algebra that's contained in that way. But then you can take the modular Hamiltonian for this, the modular Hamiltonian for that, in this thermofield double state, combine them in a certain way and get something that is a local time flow in the bulk. And so that's what we did in this paper. Well, yes. Good. Yeah. Okay, right. So what did I want to say? The reason I emphasize this sort of regular entanglement structure is there. Okay. The reason I emphasize that this is renormalizable is so naively, if I imagine sort of computing this von Neumann entropy, what do I want to say? Yeah, good. Okay, so imagine, so in this, in the Hilbert space, in the separable Hilbert space that I get when I start with a state psi like this, that's converging to the EPR pairs, crucially, that Hilbert space contains a state that I'll call a psi t, which is just sort of the infinite tensor products of EPR pairs, like this. And the thing to notice about this state is that psi t, go right tilde, psi t. So this is a consequence of the extremely regular entanglement structure of this state, which lies in that separable Hilbert space. This state defines a trace. It defines a linear functional that's cyclic with respect to the arguments. Now, if I wanted to think about this trace from this original uncountable Hilbert space, this is really a renormalized trace, right? If I tried to compute the trace of any operator in here, well, I would get, okay, okay. What would this formula give me? It would give me the trace up to, it would give me the trace of the operator up to however far it's supported. So it's supported only up to some finite n. And then it's going to give me, factors of 2 all the way out to infinity. So this thing is sort of morally this trace on the Hilbert space, on this infinite tensor product of Hilbert spaces. Good, what did I call them? HI, right? It's the trace on that sort of, those infinite products of Hilbert spaces of these. This times, and this is a schematic formula, times 2, good. So this trace is going to be infinite because eventually these operators stop acting and I'm just going to get 2, I'm going to get 2 all the way out to infinity. So this is like 2, so imagine these acted all the way up to k or something. So this will give me like 2 to the k minus n in order to renormalize that. So this thing is infinite, but when I do that, but I can remove it in a very, very regular fashion in this way. So that's what's so special about these states, is that they have this very regular entanglement structure, which allows this kind of renormalization of the trace. Okay, and so now, I don't want to take up too much time because the pizza's here, but let me just emphasize.
Great pizza anyways.
Don't rush too much of it.
And so now what I want to emphasize is that the fact that this trace is renormalizable allows us to define renormalized notions of von Neumann entropy and stuff that make the structure of these type 2 algebras much more regular than the structure of these type 3 algebras. And in particular, that connects to gravitational physics. Okay, so okay, are there any questions on this entanglement classification? I know it was a bit fast.
Okay, well, I don't know about that, but so the trace, if you take that as the trace and you take the trace of some density matrix, will that be 1?
Right, so you can, right, so in this setting, good, yeah, so for any state in that, the answer is yes, because for any states in this Hilbert space, eventually, here the density matrix would just be an infinite tensor product of density matrices, and eventually it just becomes the maximally mixed state, 1/2, 1/2 out there. And so if I take the trace of that, that does exactly this sort of 2 to the minus 2 to the minus n. That removes that. Yeah. So there's also a notion of renormalized density matrix. Yeah. Good. And it's and it's trace 1. The renormalized density matrix is trace 1 with respect to the renormalized trace. Good. Okay.
There's no notion of density matrix for type 3.
Yeah, for type 3, there's no notion of density matrix. There's a sense in which like there's the description. There's no really completely localizable description of the physics. When I add in those extra operators by taking the closure to a type 3 von Neumann algebra, those are operators that know about this infinite entanglement structure tail. And so there's a sense in which I can't completely localize the physics in that setting. I have to know something about the entanglement structure of the states. Yeah. Great. Anything else? Okay. Okay, so let me just conclude with the idea of algebras in semi-classical gravity. So what's well known, and I'll just draw this case because it's the simplest to analyze. So, what's been known for a long time is that if I try to think, gravitational physics seems to regularize the idea of entropies. So what do I mean by that? I mean that associated to the exterior region of this eternal ADS black hole, in this example, but more generally just any black hole, it's believed that there's something called the generalized entropy. And let's go with this region R. There's something called the generalized entropy, which I get from adding, this Bekenstein-Hawking black hole entropy A over 4G to an entropy of quantum fields outside of the black hole. Now, what I just argued is that this entropy of this algebra outside of the black hole is one of these type 3-1 von Neumann algebras, for which in any, there's really no well-defined definition of this, but you can imagine trying to define it through a regulator, and then you would find, as you remove the regulator, the von Neumann entropy is infinite. And so these are both infinite because, moreover, this is a statement that's true in the semi-classical limit where G Newton is small. So these are, separately infinity, but it's believed that this sum is well-defined. So the splitting is not well-defined, but this object, the generalized entropy, is well-defined. And so what that means is that if we want to think about the entropy as being associated, so why should black holes have an entropy? Well, I think one way to think about it is that we should only have access to part of the space-time. When we're saying that the black hole has an entropy, we're saying that we're one of these observers out here, or we only have access to these degrees of freedom. And because we can't see the entire space-time, there's a region of the space-time we can't see, there's an entropy associated to that, associated with our uncertainty and our inability to completely determine the quantum state of the space-time everywhere. Okay. So it's believed that there should be some information, there should be some entropic notion that it would be nice to give an information theoretic interpretation to. Okay. And in particular, this generalized entropy should make reference to what operations can we do to try to determine the state. So in particular, what is the algebra of operations that we can do in this right exterior if we're given access to quantum fields? And in this setting, I'll show that if we're also given access to some perturbative gravitational degrees of freedom, we can actually make sense of this entropy and, in a sense, regulate this quantum field algebra that was type 3 down to one of these type 2 algebras. And so this is an idea that came out of studying the 1 over n corrections to this picture with the type 3 algebra. So that was by Witten in 21. And then later with Chandrasekharan and Pennington, and also with Longo, this was done also in 22. And so, yeah, sorry, let me say these are ADS. This is de Sitter, which I'll come back to at the very end. And then also a general, for a general black hole, this was done by Jonah Kudler-Flam, myself, and Gautam Sachin for these general black holes. And in particular, these allow these, so in these cases, you're always talking about equilibrium states, but here we can talk about black holes that are not in equilibrium. Okay, great. Okay, so this semi-classical result of the generalized entropy seems to suggest that entropies are better defined in quantum gravity than in quantum field theory. And so in particular, if we have a von Neumann algebra description of the physics in the exterior of the black hole, it had better be one of these type 1 or type 2 settings, because this type 3 setting does not have any notion of von Neumann entropy, regularized or not. This one has an absolute notion, and this one has a renormalized notion. Okay, good. And so let me just say that the idea of these papers, and that was put forward in this first paper of Witten, is that there's something called the crossed product, which was actually developed in the math department here by Masanichi Takasaki. And it's the idea is that if I have a von Neumann algebra V, and I have a group of automorphisms on that algebra, then I can do a particular, I'll call it the cross product. I can do a particular construction that generates for me a new von Neumann algebra. Okay. And so there's a remarkable fact, which is the following. There's a remarkable fact, which was proven, Saki, which is the following thing, that if V is type 3-1 and G R is what's called the modular automorphism group. And V, this cross product algebra is what's called a type 2 infinity algebra. And so I just want to emphasize that this is sort of a remarkable fact. It takes us from one of these unwieldy algebras for which the entropy could not be defined even in some renormalized sense to one that admits this sort of renormalized definition of entropy. And really what this cross product is it's an algebra that acts on an extended Hilbert space. So you can imagine if V was some algebra of quantum fields originally, it acts on an extended Hilbert space that also has this L2 of the group. It acts on that and is invariant under some joint automorphism. So under some joint automorphism of this algebra, it's invariant. Okay, good. So this is a mathematical fact from 1973, and it was recently realized that this is relevant for black hole physics for the following reason, which is that imagine I am studying this eternal ADS black hole, and let's say I want to formulate everything on this particular Cauchy slice that passes through the bifurcation surface. Well, then what happens is if I'm studying this perturbatively in the gravitational coupling, there's a mass degree of freedom of the gravitational field, a perturbed mass degree of freedom, let's call that delta m right. There's a mass degree of freedom, delta m left. These are degrees of freedom of the perturbed gravitational field. And Einstein's equations just give us a constraint that delta mr minus delta ml. I'm sorry, and here I'm imagining that I allow some sort of quantum field or graviton excitations in the bulk, that this is equal to what I'll call Ft. So this is the operator, so imagine if I just had a scalar field, Ft is the operator that generates flow along the orbits of that field. So in this case, it will be the Schwarzschild time orbits by LT. Okay, good. And so this cross product comes up in this gravitational setting because of this Einstein constraint, this perturbative constraint equation that comes from studying the Einstein equations about some background solution. And so what this does is it actually imposes this constraint on the algebra of observables, and this actually implies that so gravity is a theory with diffeomorphism invariance, but when I'm doing this perturbative formalism about some background, I've broken the diffeomorphism invariance, and now the remnant of that is the isometries of this background. And so I get the isometries of this background, and when I impose those constraints that come from diffeomorphism invariance, it actually lands me exactly on one of these cross product algebras. So remember, cross product algebra is an algebra that has a group of automorphisms on it, and it's invariant with respect to some joint automorphism. That's exactly what the gravitational constraints tell us to do in this perturbative framework. Here I have some algebra of fields outside of the black hole. They need to be invariant. They need to, we have to satisfy this equation. There's some constraint from diffeomorphism invariance, and that lands us exactly on this structure. And so this tells us that there's a type 2 infinity algebra associated to this exterior for which one can go and compute renormalized von Neumann entropies and argue that the differences of those entropies look like differences of generalized entropies in an appropriate setting. I won't go through the details of that. Good, and so let me just say that here, so what's true in this case is that, remember I said that we need the modular automorphism group for this to work. It has to be the modular automorphism group. In this, so an algebra is always thermal, exactly thermal with respect to its modular automorphism group. This is a general theorem of Tomita and Takasaki. And so in this case, here the modular automorphism group is quite literally this group of, it generates these boosts on this background geometry. And so that's how it enters the constraint equations. And so that's what happens in these settings where you have exactly equilibrium states. And then what we showed is that actually you only need equilibrium in the vicinity of the killing horizon in order for this construction to work. Okay, so I'm a little over time, but let me just finish with one thing, coming back to the picture that I'm pretty sure I drew at the beginning, which is the following. So what does that mean? The fact that this seems to be applicable even only in the setting with local equilibrium, what it implies is the following thing. So if we come back to this picture, so here's us, us in quotations, if we lived all the way back to reheating, then what this implies is that because we only need some notion of local thermal equilibrium, sort of if there's a setting in which one can argue, so there's a setting in which one can argue that for this picture, which is the effective field theory description of our universe so far, and so if I take this picture, so here we have some ds of lambda, as you know, in the asymptotic future. If we imagine that we have a space-time that underwent some inflation in the asymptotic paths, then this would have some ds of lambda effective, where this is set by the value of the inflaton potential. Then what you can argue, then what this picture seems to suggest, which is the EFT picture of our universe, is that because you have this this sort of de Sitter universe in the past, if you formulate everything on an initial data surface that looks like this, then you can argue that there's some sort of approximate thermal equilibrium, so that are the observations that we can make within this EFT picture actually describe what's called a type 2 infinity von Neumann algebra. And so let me just clarify, you might have remembered when I talked about de Sitter before, I said that Chandrasekhar, Longo, Pennington, and Whitten told us that it was actually I didn't say that, did I? Okay, they told us that it was a type 2-1 algebra. That's not super important. What's really important for that is this is an algebra that admits a maximum entropy state. And this algebra doesn't admit that. And so in particular, the way that we find that in this picture of the universe that's sort of inflating in the far past, that we get this, why do we get this difference from their results? And the reason is that it's very different, it's very physically different to have a dynamical cosmological constant that's set by the value of a dynamical field than to have it just be some fixed parameter in Einstein's equation. And so what we can argue is that the fact that this cosmological constant during inflation is set by the value of a dynamical field during inflation leads to this additional sort of unbounded degree of freedom that modifies the algebra back to this type 2 infinity, setting. And this is desirable because we might worry that if we started in an algebra that admits a maximum entropy state, then we can't have any notion of any non-trivial notion of the second law of thermodynamics, because we just hit the maximum entropy, and then what do we do? But one can argue that in our current EFT understanding of this picture, we actually end up at this algebra that doesn't admit a maximum entropy state. Okay, good. And so, let me just close by saying that I think there's lots of interesting questions here, and that these algebras can give us a lot of insights, into quantum gravity, and also into this sort of emergence of these semi-classical pictures that work really well. And so a nice aspect of this story is that this is a story that started from considering the properties of large N CFTs. That's supposed to be a quantum mechanical description of, it's really a fundamental quantum mechanical description of quantum gravity. And if we follow our nose through that story, what it tells us things about these effective field theory pictures that can be applied to our universe, even outside of the ADS spacetime. Now, of course, we don't know at the moment how to get back to a fundamentally quantum description outside of ADS. And so, that's a question, is outside of ADS, is there any sense in which we can understand the emergence of these pictures from fundamental quantum mechanical degrees of freedom? I mentioned that there's this issue of the renormalization of the trace. When we give these things, I think another sort of interesting problem in that setting is if there's these sort of recent discussions of so-called space-time wormholes. What they do is they remove a bunch of states from the Hilbert space, and they give you a notion. So this is also in the context of ADS. They give you a notion of the fact that a boundary trace is not necessarily equivalent to the bulk trace in effective field theory. And so I think it would be very interesting to try to understand that renormalized trace that we get in this from this going from this type 3 to this type 2 algebra, and then understanding that renormalized trace and how the bulk trace is different from the boundary trace in that setting. Another interesting question is what about if we put in these sort of horizon symmetries or asymptotic symmetries? So here, or asymptotic. So here what we, this cross product exists you can do it for any locally compact group in this way. And so another interesting question is, in things like asymptotically flat spacetimes, it's not a great picture, but in situations like this, can we understand how to impose additional constraints that are related to these horizon and asymptotic symmetries? How does that affect the structure of the algebras? Does it give us some more fundamental description and insights? I think this is a really interesting question that we don't know how to study at the moment. Good, and then I think finally another interesting question is what we did in order to obtain this sort of cross product algebra is we had to add in some extra gravitational degree of freedom, but certainly so there should be physical effects to being able to measure things. Like in this case, being able to measure this ADM mass should have physical effects. And I think at the moment, the only thing that we understand about that is that this allows some definition of the von Neumann entropy, but we do not have an operational understanding of what it means to measure this ADM mass, and in particular from the bulk perspective. And so I think there's lots of interesting questions in this area that to still study. And that's, I think, all I wanted to say.
I suggest we carry on the conversation now with video.
Sorry.